So this is a continuation of the lecture on section 2.4 on polynomial maps. The last one kind of cut off unexpectedly, so we're going to continue with the forwards direction of the proof of theorem 2. So we're assuming now that f is in the image of phi. So that means that f is phi of something, let's call it g. Which of course is g of f1 through fm that we've seen, and now g is in our ry. Great. Okay. So now if we consider the difference of f and g, because f as a polynomial in the x variables is actually g evaluated at the f's, we could rewrite this as g of f1 through fm minus g of y1 through ym. This is in the ring Rxy. But now, using our technical lemma again, this difference is actually in our ideal A. So what this says then is that f is congruent to g mod A, which we've seen already is equivalent to them having the same normal form. So that means that f and g reduce to the same polynomial, say h, when reducing via the Grubner basis g. But now we can observe that g is actually a polynomial in only y variables, right? Since g is in our y, in order for g to actually reduce at all, the element of the Grubner basis would have to have leading power product dividing a term in g, right? So g can only be reduced by polynomials in g that have leading terms that are only y variables. But because of our ordering, the x variables are larger than the y variables. If their leading terms are all y variables, then all of their variables are y variables. So g can only be reduced by polynomials in g that are also in our y. So in particular then, if g has only y variables and it's only reduced by elements, we can only reduce it using elements that have only y variables, then h will only have y variables as well. Which is what we need. Okay, so there's a corollary, a nice corollary to this theorem, where we can just restate the theorem in terms of the normal forms. So the corollary says that, keeping our previous notation, that if f is in our x, f is in the image of phi if and only if the normal form of f reduced by g is in Ry. And now we can more explicitly answer our second question. To determine whether a polynomial f is in the image of our K-algebra homomorphism phi, we first compute a Grobner basis G for the ideal A, where A again is y1 minus generated by y1 minus f1 through yn minus fn. With respect to the elimination order, with the x variables larger than the y variables, then step 2 is we just take f, reduce it to its normal form, and see if it has any x variables. If it has any x variables, then we know that f is not in the image, and if it only has y variables, we know that f is in the image. Okay, so now we can address our third question. So our third question is about whether or not phi is onto. So first we observe that since phi is a map from Ry to Rx, if each of the xi variables is in the image, then phi is onto and vice versa. So we can use that in our classification. So the statement of theorem 3, given our same notation for A and G, so G is a Grobner basis, again with respect to elimination order with x variables greater than y variables, then we have that phi is onto if and only if for all I between 1 and n, so for each xi variable, it's another way of saying it, there exists a gi in the Grobner basis G such that gi has the form that is xi minus a polynomial with only y variables. In this case, we have that xi is equal to phi of hi, which in other terms is hi evaluated at f1 through fn. Okay. So again, to prove this, we have two directions to do, and it ends up being the backwards reverse direction. That's the easier one, so we'll start with that. So we're going to assume that we have, for every xi variable, a Grobner basis element that's of the form xi minus a polynomial with only y variables. Then what we can do is that since since xi minus hi is in the Grobner basis, we can use it to reduce the variable xi. When we do that, we'll just get xi minus hi, which will just give us hi, which of course only has y variables. So then using our theorem 2, we know that xi is actually in the image of phi. And since I was arbitrary, all of the xi's are in the image of phi, and we have that phi is onto. Moreover, again by theorem 2, we know that xi is actually equal to phi of hi, which is hi evaluated at f1 through fm. So that's the reverse direction. We still need to show that given an arbitrary onto map phi, we have this property of our Grobner basis. So first, we're going to assume phi is onto, but we can also, without loss of generality, give an ordering to our xi variables. So we'll also assume, without loss of generality, that our xn variable is larger than our xn minus 1 variable, etc., down to x1 being our smallest variable in our term order. So by theorem 2, looking at our smallest variable x1, since it's in the image of phi, since phi is onto, we know that there exists some polynomial with only, let's call it h1 prime, with only y variables, such that x1 reduces by a g to h1 prime. That means that then the difference, x1 minus h1 prime, is in our ideal A. And so there exists a g1 and g in our Grobner basis such that the leading power product of g1 has to divide the leading power product of x1 minus h1 prime. However, since the x variables are larger than the y variables, and the h1 prime only has y variables, this has to be x1. So in particular, that means that the leading power product of g1 has to be x1, supposing our map is a non-zero map. Okay, well, since the x1 variable is the smallest of these variables, and that's the leading power product of g1, g1 can't have any other variables in it except for y variables. So that's what we want, but only in the smallest variable case. So then g1 has to equal x1 minus some h1, where h1 is in our y. Okay. So we can do something similar for g2, and for x2, our next smallest variable, but what happens here then is we have that the leading power product of g2 divides x2, suppose that the leading power product of suppose that G2 had some x1 terms, right? Those are less than x2, so they could be involved. If they did, because the leading power product of G1 is actually x1 itself, those could all be reduced out. And since we're assuming our Grobner basis G is reduced, that's impossible. So that means that only y variables could exist besides our initial x2. So since we can keep doing this, we get our desired result. Okay, so theorem 3 gives us a way to specifically address our third goal. So what we do is we first, again, compute the Grobner basis for A, as before. Now what we do is we check and see if the results of that Grobner basis are of the form xi minus polynomials in y, where each xi occurs. If for each variable xi there exists a Grobner basis element that's xi minus a polynomial in y variables, then we know phi is onto, and if that's not the case, then we know phi is not onto. So that answers our question. Okay, so that addresses all three of our goals, but we're not done. What we want to do next is we want to answer the same three goals, but now for quotient rings. So for the quotient ring setting, we end up with very similar theorems, each one corresponding to our previous one, so I'll call them theorem 1 prime, 2 prime, 3 prime. I won't prove them, they're all in the book, but they mimic, the statements of the theorems mimic closely the theorems you just saw. Okay, so we want to now consider our maps phi to go from Ry mod some ideal j of Ry to Rx mod some ideal I of Rx, where again they are K-algebra homomorphisms, so they're both ring homomorphisms and K-linear transformations. So just like in the previous case, we want to know where the fundamental elements of our domain are mapped. So in this case, we'll assume that phi maps yi plus j, that coset, to the coset fi plus I. And we also want to observe, since we're looking at a quotient ring, we want to make sure that our maps are well defined. So we don't want there to be ambiguity of where we can send objects. And phi is well defined if and only if for every element in our ideal J, H evaluated at F1 through Fm, these Fi's here, is in the ideal I. So this is by the factor through lemma for quotient rings. A whole bunch of them. Okay, so now I want to state the three corresponding theorems in this setting. Theorem 1 is prime. So let A now be the ideal generated by everything in I as well as our differences of yi's and xi's. So this is an ideal in our xy. Then the kernel of phi is precisely the intersection of this ideal A with our y mod the ideal J. So i.e. if A intersect Ry is generated by the polynomial, say, h1 through hp, then the kernel is the ideal generated by h1 plus j through hp plus j. Okay. So that addresses our first question in this quotient ring setting. So our second question is to determine when an arbitrary coset is in the image of our map phi. So as before, we'll let G be a Grubner basis for A with respect to an elimination order with the x variables greater than the y variables. Then, if we consider some element f plus I in the quotient ring R x mod I, we have that f plus I is in the image of phi if and only if there exists some polynomial in only y variables such that f reduces by a g to that polynomial h. And again, in this case, we have that the coset f plus I is equal to phi evaluated at h plus j, which is h of f1 through fm plus I. As before, we have a corollary of theorem 2 prime in terms of the normal forms. We'll call it corollary prime. So with same notation, we have that for f plus I in our quotient ring, our x mod I, we have f plus I is in the image of phi if and only if the normal form for f with respect to g is a polynomial in only y variables. Okay, so we have one more theorem to state, and that's the corresponding theorem to theorem 3. So this will be theorem 3 prime. We have the same setup with the ideal A and the Grobner basis G. So this theorem determines when phi is an onto map. And we have that phi is onto if and only if for every x of I variable there exists a element of the Grobner basis that's of the form xi minus hi with hi a polynomial in only y variable. So just like in theorem 3. Okay, so that concludes the section 2.4 discussion, and when I come back into town we'll have our homework 3 day on Friday, and then we will get into some fun applications with recoloring and Sudoku and other number puzzles.